and left ventricle. So, in this diagram you have the oxygenated blood that is shown by the red color. So, oxygenated blood will enter from the pulmonary vein to the left atrium, and from the left atrium by the action of the valve it comes to the left ventricle, and then from there it gets circulated by the systemic circulation. That means over the entire body, that circulation which takes place, which distributes blood to all of the body's tissues, and then it returns deoxygenated blood back to the heart. So, it is coming at the right atrium, and then the valve allows it to come to the right ventricle, and then from there the deoxygenated blood is pumped to the lung, where the purification through oxygen exchange will take place. So, this is the overall thing, and that is how the heart and lung are very strongly connected, and because really these are lifelines of human survival. So, in this particular course we have kept the cardiovascular and the lung flow, pulmonary flow, as two of the major example areas. So, now when we talk about the circulatory system, there are so many arteries, veins, etc., and every artery, vein is very unique, and it is not possible to give examples of all. The idea is that we give example of something which is very important and at the same time not very well discussed commonly. So, the example that we talk about here is carotid artery. Carotid artery, these are major blood vessels which provide the brain's blood supply, and that is why these are very critical. So, if you look, if you talk to any cardiac expert doctor, they will talk about two major types of arteries. One is the coronary artery and then the carotid artery. Coronary artery is more commonly talked about, being the main ones which come out of the heart, but the carotid artery is no less important because its disease causes up to 1/3 of all the strokes. And as I discussed earlier, the stroke is different from heart attack, that it is just something that blocks blood to flow to the brain. So, now if there is a carotid artery disease, or as a matter of fact any other similar artery disease, what will people do? One is that possibly by some symptom people will try to guess, but symptoms are usually vague, and vague in a sense that they can be very similar for many other diseases, like people may feel dizziness or suddenly fall unconscious for some time, they may feel tired. So many other types of symptoms are there which you cannot specifically say that it is for carotid artery disease. So, those symptoms may be triggering for you to go through some diagnostic test. Now, depending on what resource you are having, or to tell it more clearly how much money you are having, you may be subjected to different types of tests, and you may actually go through those, like MRI, Doppler ultrasound, and some invasive diagnostics. These are very much possible, but although these are quite advanced diagnostic technologies and they give a whole lot of information which just a ECG type of thing cannot give, but they also have their own limitations. So, this is the difference between doing an instrumentation for human body thing with an engineered thing. For an engineered thing, the instrumentation can be used to get a whole lot of other information, because an inert thing can be probed as you like, I mean that will not disturb anything. Human body you cannot just probe like as per wish. So, MRI is good, but it does not have the spatial and temporal resolution like what you get in a CFD solution. Doppler ultrasound, it has some issue with this acoustic window limitations, because it depends on the ultrasound. Invasive diagnostics are there, that means you use invasive procedure. So, you need to use this catheter, and now these are expensive. Not only that, nobody will usually like to go for that, because they have certain trauma and all, people feel somehow tensed once they have to go through these tests. And whatever are these tests, you are not able to get any detailed hemodynamic parameters such as wall shear stress, deformation, etc., which are very, very important. So, if you talk to any cardiovascular doctor, it is quite clear that the doctor is not an expert in fluid dynamics, although I have seen quite a few cardiovascular doctors who do not understand less fluid mechanics, but they may not be knowing all those mathematical tools, because they have not formally gone through the procedure, but they have a reasonably good understanding. But for their day to day practice, they need 3 important hemodynamic parameters, which in their language is pressure, flow and resistance. So, pressure and flow we understand, and resistance is like a cumulative effect of wall shear stress. So, pressure, flow and resistance, it comes from the corresponding electrical analogy, where pressure is like voltage, flow is like current and resistance is like resistance. So, these are, as you understand, these are gross terminologies, like when you say pressure, pressure may vary from one point to another point, flow rate may also be different in different branches, and resistance is of course locally varying, because wall shear stress is locally varying. But usually this kind of information is completely absent. So, for doctors, even average value of these are very, very meaningful, because usually they have no values to discuss about this. So, to get those, CFD is important. We have seen that CFD can do fluid structure interactions, but the CFD requires inputs. So, if you take some sort of branched artery as your geometric model and put some boundary condition and get a result, you will get a result, but that will not have anything to do with any specific patient. That is something, a generic thing, that is also very important for learning the science, because learning the science does not have to be patient specific, it is just the learning the science. But when you apply it for clinical application, it has to be specific to a patient, it cannot be generic. So, specific to a patient is what you get from these, at least the medical imaging techniques, typically MRI, CT scan, etc. So, when you have these data, the important point here is that can you use that data in CFD, so that it becomes patient specific CFD. So, the entire direction in which this subject moves is like, how can you apply your generic knowledge of CFD to make it patient specific CFD, and that is what we are going to talk about for the remaining. So, connecting medical imaging with mechanistic simulations. I have purposefully written it mechanistic, because it has both fluid mechanics and solid mechanics, so not just CFD. So, to do that you need a medical image. So, usually the medical image from which you get a geometric idea of what is there is the CT scan or MR angiogram. In the cardiac space, MR angiogram is very, very common. So, it is similar to MRI, but applied specifically to this cardiovascular pathways. So, this is one particular set of image. We have a collaboration on this topic with the University of Melbourne and the collaborating professors group, Professor Andrew Wee and the collaborators. They have this access of these kind of images, repository of these kinds of images from their hospital. and there is a very strong group in the hospital who are working on these, and we interface with them for this kind of research work. So, this you have. Now, there is a very important step which will convert this medical image to a geometric information or a geometric set of parameters which can be meshed for your computational simulation. So, you need to create a geometry, this is called as geometric reconstruction, because this will have some idealization. So, you take the shape and put in elements to fill up the shape and smoothen it, so that it becomes that domain only, but with a few idealizations, which is not really exactly that, but more or less that one. Then what you do is, what are the inputs that you are going to use? So, there is a very advanced technology which is called as 4D flow MRI. So, this is such an advanced technology that even most of the very resourced hospitals also do not have this. So, 4D means you have the 3 dimensional in space and also time. So, what this gives is like the fluid mechanics inside these things as visualized. So, it can give, for example, not really the velocity profile that, but flow rate at some locations and how the flow rate changes with time. So, this also we use the resources. So, it is an imaging, for example, in what you see here is a 3 Tesla MRI machine with 60 channel coil, and the ECG gating was used to acquire the data, and there the imaging is following some injection of certain contrast agent to get the clear view, and what you are getting out of that is at a given location the graph of flow rate versus time. So, that is what you get, that means data which you can visually show in the graph. So, then what you are going to do with this? So, you have MRI images or 2D phase contrast MRI images, you use, so for MRI images you can construct the geometry, and 2D phase contrast MRI will give the flow data. So, you can get the flow boundary condition. So, you now have a geometry and you have a boundary condition, and if you have reasonable idea on the properties, you can do the fluid structure interaction simulation. Now, here we have put 2 different items, one is 3D modeling, another is 1D modeling. So, we all know that 3D is the reality, right, 3D is the reality, but it is expensive. That means, if you want to run simulation in such a 3D geometry, it may take time, and if it is taking time, a doctor is not going to write a paper for which doctor is going to wait for 2 days to really get a result on the patient and do it. I mean, doctor may as well write a paper on the patient's case, but for the doctor it is more important to save the life of the patient first and then write the paper. Unlike us as academicians, we first write the paper and see whether the bridge falls or bridge is there. So, now when we do this, we have to see that can we do something which may be a bit inaccurate, but much faster. So, can we convert the 3D picture to an equivalent, at least locally 1D picture? That means, it is not completely like a sort of a straight pipe, but locally pieces of such 1D capillaries. So, that is called as 1D modeling, and because 1D is not really the order is 3D. So, converting that 3D to 1D is also known as reduced order modeling. So, somehow you are reducing your sort of dimensionality. So, while doing that, and this is what I always like to do, that sometimes there is always a temptation that you have some high end items and you present the high end items, but this is like a course. So, I can just present the high end items and you can say, oh, this is fantastic, but this is not the way in which a fundamental understanding of what is going on should be developed. So, what I have tried to do within this limited scope, at least to show that how from the most basic principles that anyone going through a very serious course on fluid mechanics will know, how can you come to this kind of problem and try to solve it. So, this is something which is a principle of conservation and transport with which we started our foundation topic discussions. So, let us say you have so this is a symbol of channel of varying cross section. This is a very simplified view, not that our blood vessel is not like that have a tapering thing, it will have some different thing, but this is just like a simple drawing. So, you have something which is the system is a control mass system, that means something which is a fixed mass. So, the system is shown by the green dotted line. So, it is a collection of mass which at time equal to 0 is coincident with a region which is that red dotted line, which is your control volume, that means your fixed place. But after some times at time equal to T0 plus delta t, the system, which is the Lagrangian concept, it has moved to the new green line. So, what we can say is that if we keep now the control volume, so if we now consider the intersection of the initial configuration of the system and the subsequent configuration of the system, the common part of that we call it as a control volume. So, you can see here that we now have the control volume and you have whatever is the left of that is 1 and whatever is the right of that is 2, and as per the direction in which the mass is moving, across 1 mass is entering the control volume and across 2 mass is leaving the control volume, and we are defining capital B as any extensive property. That means a property which is for the total mass, that is mass, volume, momentum, energy, etc. And we also define small b, which is the capital B per unit mass, that is called as intensive property. So, with this definition, what we are trying to do is we are trying to relate the change of the control mass to the change in the control, change in the control volume. So, at instant t you have the system and the control volume, just they are coincident, but to make the drawing look clear, we have separated the green colored thing and the red colored thing, they are coincident at some point of time. At t plus delta t it is like this. So, at t they are coincident, at t plus delta t, if you see the last equation, which is equation number 2, your B of the system is B of the control volume, which is the red colored thing at time del t plus delta t, minus your B at 1 at t plus delta t and plus B at 2 at t plus delta t, right. So, what you are talking about is it is just the drawing, that means that you are having this green colored thing, the new green colored thing is what you have in the control volume, which is there the diagram at the top, from that you subtract 1 and add 2, right, that is what is there, simple drawing is represented there in the figure. So, now just a minute. What we are trying to do is to see the change in property in the system, how it relates to a change in property in the control volume. So, the property of the system at time t is same as that in the control volume. at time t plus delta t we have just seen equation 2. So, we have written that. So, you subtract these two and this will give you the change in property of the system. Why we are so much interested about that is anything related to the system which is the control mass system, you can relate it with the Newton's second law of motion, because that is what in the Lagrangian framework is how the Newton's laws are stated. So, you subtract and divide by delta t and take the limit as delta t tends to 0. So, you get the left hand side we are writing it as we can write it as total derivative. Why? Because it is the rate of change with respect to the system, but we will write its expression with respect to Eulerian variables. So, anything which is fundamentally Lagrangian, but we are expressing it through changes in the Eulerian variables, usually we use the total derivative. Right hand side, the first term is at a given location how the b changes with time. So, that is partial derivative, because the location is fixed, and the last two terms, one is the rate of outflow and the other is the rate of inflow. Okay. So, you have the change within the system equal to change within the control volume plus outflow minus inflow. Now, if you write what is capital B, capital B you can integrate over the volume. So, if you now substitute that, and outflow minus inflow you can write in terms of a flux. So, V dot n is the normal component of flow over that area dA. So, that is the flow rate, that means velocity in the normal direction times the dA. So, the volume flow rate is the velocity in the normal direction times the area. So, V dot n, that into dA is volume flow rate, that into rho density is the mass flow rate, and small b is per unit mass. So, whatever is the last term, that is giving the net flow of the property B, that V dot n is positive if it is outflow boundary and negative if it is inflow boundary. So, automatically that out minus in is taken care of by the dot product. So, separately plus and minus is not written. So, this is what is known as Reynolds transport theorem, and whoever has done fluid mechanics has done it, but I thought that it is good to just recapitulate this. And the whole idea is that we are trying to express what is there in the system with respect to the change inside the control volume. Now, we will apply this to something, this red colored thing we imagine as a length piece of a blood vessel. So, the length piece of the blood vessel we consider from Z to Z plus delta Z. Locally it is like a unidirectional flow along Z. So, now if you apply the Reynolds transport theorem, conservation of mass, then capital B is the mass. So, if you substitute that, and so it is the dm dt, right hand side first term is partial with respect to time, whatever is the mass inside the control volume. So, that is that one, the integral of this ds into delta z is the volume, that times rho is the mass, and the flow term is the next term. So, we are just using the Reynolds transport theorem. Now, conservation of mass is that if you have a control mass system, a system of fixed mass, the mass is conserved. So, that is 0. Then you have the right hand side what is called as the unsteady term, and the last term is the net volumetric flow rate, because whatever is coming out and going in. So, that is basically due to the net change in the volumetric flow rate. So, that is delta q. So, you divide by delta z, delta z was that axial length, you want a local value. So, you make that axial length so small that it becomes a point. So, divide by delta z and take the limit as delta z tends to 0. So, this what you get is the so called area averaged continuity equation. So, this is the continuity equation, but area averaged. And then you go for the linear momentum conservation. So, you can write the force as your capital B, and in the z direction if you are talking about your writing this equation, you write the z component. So, momentum is just the mass times the velocity. So, uz has come and mass expression is the same, and what we are also going to note that the right hand side what you are seeing the last term, that is the outflow minus inflow, and outflow minus inflow is due to the change of u as it has gone from z to z plus delta z. So, u z plus delta z minus u z is responsible for the differential flow, and that you can write in a Taylor series expansion, and we may keep the first term only, and again you can substitute that in the right hand side. So, you will get this one, this what is the net this flow when you are talking about outflow minus inflow, that is u z plus delta z minus u z. So, when you write that, so that is your net force. Now, the net force, so the right hand side in the top what you have written is the unsteady term and the advection. So, this is basically mass into acceleration, and that is equal to the force. So, force is due to two things, one is the pressure gradient. So, if you have the pressure gradient there, then the pressure gradient which is acting. So, you can imagine that you have the pressure acting on the area this ds. So, pressure which is acting on the area ds, and the effective pressure, the change in pressure. So, what you are talking about is change in velocity, similarly change in pressure. So, change in pressure just like the Taylor series, just replace u with p. So, that is that pressure gradient with respect to z into delta z. So, that is your difference in pressure, that times ds is the force. So, that is the force due to pressure, and you have a force due to the wall shear stress. So, tau wall is the wall shear stress, and the area on which it is acting is so if you have a circular thing and the wall shear stress is tau wall, and if the radius was constant, then the area on which this is acting is 2 pi r into delta z. But if it is not circular, instead of 2 pi r it will be some perimeter. So, we call that L. So, L is like 2 pi r. Okay. So, now you can equate the left hand side with the right hand side and you can get this equation. You can simplify it further and I will show that. So, now your objective, we are continuing from the previous this slide. So, wall shear stress you have to calculate, and this is where you require the velocity profile. So, to get the velocity profile, let us assume that u by u average, that is the velocity along z divided by the average velocity along z, is a function of your local radial coordinate r. So, if you now substitute that velocity profile, so if you know nothing, you can use your approximate parabolic velocity profile, which we have learned from that Hagen-Poisson flow. So, that in that case f is 2 into 1 minus small r square by capital R square, that all of you have done basic fluid mechanics will know this. So, this is an example, but see, always there are so interesting scopes. So, if some of you are interested, you can say no, in real artery vein this will not be the case. So, what will be the case? So, you can take a better approximation. Someone will say no, why should I take a better approximation? Let me get some data from a 3D simulation of the geometry used for real patients. So, some of those who are really interested will then ask a question, okay, but how, where will I get that real patient data? What we very commonly say, where there is a will there is a way, and this is something like this. You do not have to go to a hospital to get patient data. So, there are huge repositories of open source data. That open source data is there for two things, one is clinical research and even for fundamental research, where you do not know the name or whatever, I mean it is decoded, but you get this. So, what one can do is that if you get such data, then apply data science to use that data to get a number crunched equivalent of the 2 into 1 minus r square by r square, right. And then if you substitute that in this model, see this is why it is very important, say people who are doing in the modern era data science, if they want to apply it for a good physical problem, it is very important to understand the basic of the problem. See, I could have told you what the equation comes at the end, job is done because you can solve that equation, but you will never know where your new thing you will put if you do not know how it is derived, and that is why these fundamental derivations are very important. In your life, if you want to progress in research, never ignore the fundamental derivations. There is always a tendency to do that because you can plug and pick, somewhere something, the so called formula, and from our junior days we are very happy to see a formula, because formula you put value you will get answer, but that is very good for your so called exam life, but it is absolutely a disaster for innovation to do anything. So, here there is a scope of innovation, that you replace this 2 into 1 minus r square by r square with something realistic, which in the old era would not be possible to be as realistic as currently, because now you have medical imaging data, now you have data science to convert that to a number crunched function. So, instead of this f you could have another f, but if you have this f and then if you integrate, then you will get things which are functions of f. So, if you replace, see whatever is there at the bottommost, this is still very general, and only your very good choice of f means your job is done, because otherwise there is no approximation. What is there is you have integrated your governing equation over the control volume, and that is alright, I mean there is nothing wrong with it. So, in that integral expression, the only approximate thing which is giving you an approximate answer is the velocity profile. So, if you have by some way a means to give it quite well, your answer also will be quite well. So, with this particular example you can now have this velocity profile, and so with this velocity profile you can do the integration analytically and you will get that equation which is there at the top, and in that you have a velocity gradient at the wall, and to get the velocity gradient at the wall you integrate the continuity equation in the differential form, and from there you will get the value of velocity gradient at the wall in terms of the average velocity. And why average velocity is important? Average velocity is simply the flow rate by the cross sectional area. So, you can write everything in terms of the flow rate, which is your, as I told, the interesting hemodynamic parameter for a doctor, pressure, flow and resistance. So, once you do that you get your so called final formula, and this final formula is based on the f. If you change an f it will be a new formula, but this is absolutely general in that way. So, the summary is that now you have two equations, one is the area averaged continuity equation number 1, and number 2 is the area average momentum equation, which we have just seen how it is derived. So, we have assumed a parabolic axisymmetric profile. If you have anything different, you will have the algebra different, but method the same. Now, this does not close the model, because you also need a physical law that will relate the pressure with the area or the radius. Yesterday I gave you a homework where I mentioned that for a thin walled cylinder, say you have that formula, the hoop stress sigma is P into R by T. Okay. So, in that way, so that means you have the stress proportional to the pressure and it is also proportional to the radius, local radius. So, here the local radius itself is also a function of pressure, right. How do you, if you recall that in that micro channel problem, how did we do it? We applied the equation of equilibrium for the solid part of the domain, integrated it and got the displacement, and that displacement we related to the pressure. From there we got the expression, and displacement will be a function of that modulus of elasticity, etc. So, a similar thing when it is applied here for a linear elastic fluid, it gives, so it is exactly the same as that one, and square root of S is because like we are talking about radius, and radius is proportional to the square root of the cross sectional area. Perfect circle is pi r square, right. So, that is how the square root of S comes. So, once you do that, so this is what is like a constitutive behavior, that means how pressure varies with local area, local thickness of the blood vessel and the modulus of elasticity. So, with this you can solve these coupled equations. The advantage is that now this is a one dimensional unsteady problem and you can solve it in a much less computational time. Whatever may be the method, time will be much less as compared to the 3D solution. So, computationally much expensive, much less expensive, and it typically takes less than an hour to complete even that carotid artery problem. So, quite straightforward. So, if the doctor gets MRI input and somehow can translate that as some boundary condition to the 1D problem, we will see how it can be given. Then to get the Q, the doctor maximum has to wait for 1 hour, which is not bad, because any investigation the reporting time is not less than 1 hour anywhere.
Sir, since here you are approximating it as a parabolic axisymmetric profile, that means you are ignoring the region where flow development is occurring. So, is there any way how we can choose that region for 1D reducing?
No, you cannot choose, simply you can approximate. So, region you cannot choose as per your liking, because your region is a full this one, full your zone, say some you have main artery and some branches are there. So, you can only consider that region for which you have input knowledge about the input inflow and the outflow, which comes from the MRI thing. So, it is not as per your wish, that is what I say. No, it is very different from an engineering world, where you say I have a long pipe, I will take a part of this which is fully developed. So, here you do not have something like that. Whatever is available you have to do it, and whatever is approximate you have to be careful about it. So, clearly it has limitations. What are the limitations? The assumption is a parabolic velocity profile. These may not be valid for all scenarios, as I have discussed. So, if you have boundary layer separation, or you have some maybe branching. So, you have main artery and then you have branches. So, at the junction you will not have parabolic velocity profile. So, there will be some there will be some error. Not only that, you may also have a local recirculation, which will not keep it unidirectional flow. So, assume only flow is along the z direction, but you will also may have some flow in the theta direction, at least wherever there is local recirculation. So, those things will give errors, but where we can still manage is that this is an integral form. So, integral form, the advantage is that if there are a few local errors, when it is integrated over the entire domain, that error is not significant. So, imagine that you are just try to relate it with your basic understanding of calculus. Say you want to calculate two things, one is a function f, another is integral f dx. So, when you have the function f wrong at a point, that means it is wrong, and the wrong may be very severe, but integral f dx, let us say at 1 or 2 points or a few points you have f wrong, but integral f dx is area under the curve over that entire thing. So, the total area under the curve may not suffer that much. So, that is why integral form engineers always like to use, because it somehow masks your ignorance about many things which you actually do not know, and integral forms are very popular like boundary layer theory and so many other things people, that is why they prefer the integral forms. So, now you enter to a real scenario where you have a patient data. So, we are now getting into that how we can use the patient data to form either the 3D model or even the 1D model, that means geometrically and in terms of boundary conditions. Equations we have already seen. So, what will now be needed are the geometry, boundary conditions and properties. So, let us say you have this internal carotid artery. So, the carotid artery will have some branches and their names are written. So, why their names are important, because sometimes doctors refer to these names to really say where the flow rate, where the pressure. So, it is a good idea to at least recognize the names. We do not have to remember this as an engineering analysis, it is just some branch. So, now the interesting part is that, so you can smoothen and do all this. For a one dimensional calculation, what you can do is that you can forget about that 3D structure and just extract their center lines. So, that will be like a local 1D, and there is a open source software very popular which does it, known as SimVascular. So, the SimVascular will create that line diagram of this, and for each of these lines you can apply that equation. So, it is just like you imagine the complex pipe system as a network with a node and something is going in and something is going out. So, that you can use a kind of Kirchhoff's current law, voltage law type of thing. And the flow rate versus time at the inlet is given by the phase contrast MRI, which is for a particular patient, an anonymous person. This is Q versus time. These are all practical data from some humans, but that is what. Now, this is for the inflow. For the outlet, what you do? For the outlet, you do not have really anything, any information, and there are quite a few sort of branches through which it is coming out. So, it is usually split in 3 different for the carotid artery, 3 different branches, and as obtained from the MRI, it is one of the branches is 70%, another 25%, another 5% for the 3 branches. Total you will have 100% of the outflow. The mean pressure you can, you have no idea, but the artery's mean pressure you can get from the cuff blood pressure measurement. That is the classical blood pressure, or you maybe by a digital thing. So, for this patient it was this value, and typically what you require is not the average value, but the waveform of the pressure. Pressure has a variation of time. Now, fortunately for general human beings, I mean except for exceptions, that waveform is very similar. So, if you, so that means you have a sine function or a cos function, instead of sine cos it is something more involved, but such a periodic function. So, you can set up the function correctly if you know the mean and you can set the amplitude. So, that is set by that 90 millimeter. So, you with that reference you can set up that function, because that is more or less like universal, not really universal, but you can use an approximating function. The original patient specific pressure waveform, it is possible to know, but for that there is an invasive guide wire based procedure, very tough on a human. So, invasive procedure, and then from that pressure versus time is known. Usually no person will allow you to do unless sort of you are so in the mercy of the doctor. Say someone has heart attack and all, and doctor can do anything on the person to save the life. Otherwise normal human person will not like to go through this diagnostic test. So, this approximation by just the blood pressure measurement and using an approximate function, it may sound to be bad, but it is not that bad, because you have to see that in a non-invasive way what best you can do. Now, at the outlet, the boundary condition, be it 1D, 3D, etc., this kind of lumped model is used. As I told you previously, and in one of the very early study, maybe the first session, that due to the work of Otto Frank, the distensibility of the blood vessel was thought of, imagine like a capacitance, capacitance stores charge and this stores volume, and resistance is resistance against flow. So, there is accordingly the outflow has been approximated by a lumped model where you have two resistances R1 and R2 and one capacitance where C and R2 are in parallel. So, this is commonly known as RCR model, and it is very well established, and there are ways of calculating R1, R2 and C depending on what you get from the medical imaging and the blood pressure data. So, R total is R1 plus R2, which is the mean pressure by the mean flow rate. So, mean pressure is also measurable and mean flow rate is also measurable, because flow versus time you get from the MRI, phase contrast MRI. Physically R1 represents the proximal resistance, proximal means what is the close, and R2 is the distal resistance, and C the compliance, which is like the capacitance. So, R1, R2 and C is found by minimization of the target pressure wave and pressure wave estimated from this. So, this is, how do you find this out? These are all artificial parameters. So, you have a pressure wave which is physically there for that person, and physically in a sense invasive procedure is exact, and by measuring the cuff blood pressure and then approximating it by the physiological function, that is also physical, and this 3 parameter model will give a pressure which is an artificial. So, the difference between these two, if you minimize, then whatever parameters R1, R2 and C you will get, that is like equivalent resistances and capacitance, which will give the same pressure profile. So, if you do that, so what you do is simply you use the Kirchhoff's current and the voltage law. So, you have the total voltage as, so if you see that whatever voltage is there in the from the left side, which is in the right side, you have the voltage across the, so in the right hand side what you see, Q by C into 1 plus R1 by R2, it is representing the voltage which is across the capacitor, and R1 into dq dt is the voltage which is the voltage drop due to the current in R1, because current is dq dt. So, sum of these in the right hand side is the total voltage drop, as you, if you are traversing the path, the current, the charges are flowing along R1, then the charges are stored at C. And similarly in the left side, the same is the voltage across this, sum of these dp dt, which is that you have the node, the first node, and then if you imagine that the flow path through R2, then that is P by C R2. So, irrespective of the flow path, the total voltage drop is the same, and that is how they are equated. And Kirchhoff's current law, total current is the sum of the currents that are there at the junctions of these. So, if the total current is flowing Q, that is the right hand side, in the left hand side is distributed, one going to C and another going to R2. Okay, so, this is what it is, and then you do all this algebraic manipulation and you get a differential equation, and you can integrate it by an integrating factor, because it is like dy dx plus py equal to q. So, if that form of ordinary differential equation, you can use an integrating factor, and with that integrating factor you can get an expression for the pressure versus time. where the parameters are R1, R2 and C. So, your objective is to make this pressure versus time match with what is measured from the person and then accordingly fix up R1, R2 and C by that method that I talked about. So, once you know that, then you have a fluid structure interaction problem. If you are solving a 3D problem, I am not going to repeat this because we have discussed about this extensively. So, you have a fluid domain, you have a solid domain, and what is done is that if you are considering the fluid and solid domain as continuous, whatever is the interface force between the fluid and the solid, that you dump in the form of a body force in the solid mechanics, which is the surface traction divided by the wall thickness, and the stress strain is linear for the solid. So, it is linear elastic, and for fluid this is Newton's law of viscosity. You may argue that blood is a non-Newtonian fluid, so why Newton's law of viscosity? For large arteries that approximation is not that bad. So, always keep in mind that for large arteries it is the elasticity of the artery that should be your main concern, and for the small blood vessels it is the non-Newtonian nature of the blood. So, these are some results, so this is something what you can present to the doctor, the so called colored fluid dynamics. So, this is important because I mean you have to do two things. One is you have to give the doctor something useful, and you have to also give doctor something impressive. So, you cannot just sort of give some tables and very what you say blunt looking graphs. So, you give something like this, and with all the modern tools you sort of superimpose one image with the other and make a movie. So, doctor will see how this wall shear stress is changing with time like an animation, and doctor will say, wow, now this is an engineer whom I was looking for. So, and then as an engineer your job is not to make the doctor fooled, so that this value is correct and doctor is also impressed. So, this is the oscillatory shear stress, and this is how you calculate it. Why this is very important? Because this is giving a value of the shear stress sort of averaged over the time period, and that is very important because at every time it is not important. And then you have this displacement and wall shear stress. So, that is this how you impress a doctor. So, all these simulations, these animations going on, and with these properties. So, now the question is, well, you have put certain things, how good are these inputs? So, this result is quite good. You have done everything, you have taken medical image, you have taken flow from that, but properties you have not taken from that. Young's modulus, who will measure Young's modulus of the blood vessel wall, right? So, you can try to do an experiment on your friend, put some anesthetic and try to measure Young's modulus, good luck. So, if you can do that, so that is not there. Density of blood is more or less, yeah, I mean this is not very bad, whatever it is, and viscosity is like this is apparent viscosity, treating it as Newtonian over that is also okay, and wall thickness, this is also not that bad, but again it can be usually anything between 1 to 10 millimeters. So, 2 is something which is again some approximation. So, there are two important uncertainties, Young's modulus and wall thickness, and so whatever you get you have to at least tell your doctor very candidly that doctor, I have given these with these uncertainties. So, doctor will say then what I will do with this. So, you have to then give the doctor a feel that if these uncertainties were covered with maximum and minimum range, what would be the difference in the answer, and the doctor then will have a confidence that okay, maybe this is told that this is the answer, but even if it is inaccurate, this is the upper limit and this is the lower limit. So, we will see how that can be done in the next session, but if you now compare the 1D and 3D, see it is not that bad, and for rigid and deformable channels the symbols are different, you can clearly see. So, there is a decrease in the peak value of the pressure with increase in deformability. This is qualitatively we observe, and the reason is that increase in the diameter of blood vessels due to increase in compliance reduces the hydraulic resistance. So, these are with values of density, viscosity, and thickness as 10% of the radius. So, this is approximately the order of magnitude wise correct. Local radius, the local thickness is about 10% of that. But again, if you have plaque formation and all, that is a different thing altogether. So, to summarize this session, the full scale 3D and 1D reduced order modeling simulation of blood flow through carotid arteries is utilized to find out flow rate, pressure, wall shear stress, oscillatory shear index, etc. And 1D reduced order simulations, they could be completed in even minutes on a single CPUs. They could be practically very useful for healthcare, for real time prediction of what is going on for a particular patient. And you have indeed significant variations between rigid and deformable vessels. So, this gives the at least the justification of doing a fluid structure interaction analysis. So, we stop here in this particular session and we will move to the next session in about 5 minutes, where we will see that now that we have seen that what physics can do, we have also seen that what physics cannot do. So, where you do not know data, you are limited by your lack of data, although your physical law is correct. Physical law is Newton's second law, not that for human body Newton's second law becomes some other law. But because of your lack of knowledge in many complex matters which are there inside the human body, they are occurring, you are bound to get something which is not relevant to clinical practice. So, how can we convert all these and maybe some measurements that we do in the diagnostic tests on a regular basis when we consult a doctor, to make something which is more practically relevant for a doctor to take a decision, and that is where you will see how physics and AI can be combined, and that we will see in the next session.